I guess we can start. All right. Hello, everyone. Thanks for coming to this talk. So by the end of this, you're probably going to think I am slightly crazy. So I'm going to talk about how Postgres is not just a great database, but potentially also a great distributed computing platform. And well, why would that be useful? Well, a lot of companies, when they start out with this being their architecture, their data architecture, right? You put your data in Postgres, and you actually have a lot of flexibility. If you need to build new features, new applications, you can build that by maybe making some new queries, new tables, new views, new indexes on Postgres. So this gives you kind of the flexibility that you need as a young starting company. But then as things grow bigger, this tends to happen, right? You deploy system on system on system to kind of deal with large flows of data and process them. So you might end up with HDFS and Kafka and Spark and Mongo and Redshift and S3 all combined into one slightly messy architecture. And the operational cost of such an architecture is quite high. I mean, you have to deploy and maintain all these different systems. But you also have to, you might not know them very intimately, all of them. So tuning them becomes quite difficult. So you're probably going to spend more on hardware than you would like to. And you're going to spend a lot on operations. And you don't really have a lot of flexibility, right? You can, every time you want to do a new thing, you might have to actually deploy a new system. So what I'm kind of crazily proposing is that your data architecture could also look something like this. And there's companies out there that do this, where all your systems kind of are built on top of Postgres. Did the sound cut out? Hello? Yeah, OK, thanks. So like, if you know Postgres very well, then you can make sure you tune it well. And if all your systems are kind of based on the same infrastructure, it becomes much cheaper to operate. And moreover, because it is Postgres, you actually keep a lot of the flexibility that you had when you were just a small company with a single node database. And I would argue that Postgres is actually a perfect building block for creating distributed systems. Whether you're like considering writing the software for a new distributed system, or even just need to solve a scalability problem, I think Postgres is a great way to get started. Because Postgres has really a lot of the important features that you need when building a distributed system, which often take like 10 years to implement. Like a lot of systems, before they have a well-defined, extensible, efficient protocol that supports batching and asynchronous execution, it takes many years. And Postgres has it. And you can create new types that can get serialized and deserialized. Crash safety. One of the most important things in distributed systems, and a thing that most systems get wrong the first 5 to 10 years. So if a node crashes and comes back, you don't want to suffer from your files getting truncated. And Postgres, this is almost Postgres' core business to solve this problem. Concurrent execution, like another thing that even a lot of NoSQL databases still don't really get right. And Postgres is actually arguably one of the best databases for concurrent execution. Transactions. So last year at PGConf SV, I gave a talk about PG Paxos. And I argued, actually, implementing Paxos on top of Postgres is relatively easy, even though Paxos is known as quite difficult to implement. And the reason is that on Postgres, you have transactions. And the difficult bit about implementing Paxos is that you kind of have to build a database. You kind of have to make sure that whatever promise you make in the protocol is actually kept, even if you crash. And you need to deal with concurrency, and you need to deal with other things that Postgres solves for you. And so Postgres has a lot of features that help you kind of set up a distributed system with also 2PC and replication, and also custom functions. You can just put like program custom logic in Postgres. And the other thing is extensions. And some of these extensions already kind of usually ship with Postgres or come as contrib modules. Like Postgres FTW lets you query tables that are on a different server. dblink just lets you send like raw commands to other servers from a SQL query. And PGSQL and also the other procedural languages kind of let you tie everything together. And then there's third-party open source extensions, such as pglogical for logical replication, pgcron, kind of a pet project I have, and Citus, which actually, if you start combining them all, you can do very interesting things. So I really sorry. And of course, there's your extension. It's actually not so hard to write a Postgres extension. I'd advise just take one of the existing extensions, rip out the code, and use that. And so you can combine that with all the existing extensions into one system. So one of my favorite tools for doing this is dblink, especially for prototyping. Like, it's so useful. You can just connect to another server, send a query to it, get the result, and disconnect. And it can also send queries asynchronously, so you can open a couple of connections, send a couple of queries asynchronously, get the results, which means you actually can do parallel execution, just using a couple of SQL queries. And also, perhaps more importantly, you can do remote procedure calls. So you can create a function on one node, and then create like a client-side stub using dblink on another node to call that remote function. And RPC is usually kind of the building block for a distributed system. PGSQL is then super useful for tying these kind of things together. So if you want to get, you have a lot of databases, let's say you want to get the size, you can write a simple function that kind of queries all these databases in parallel and sums up all the sizes. So we can, like, these things become quite interesting when you combine them. And just with these extensions, we can already put together quite an interesting distributed system where maybe I have nodes in which I continuously shove some data. Maybe there's a central kind of authority which keeps track of which nodes are in the system. And then maybe I use PostgreSQL to be able to read that nodes table on all the other nodes. And then maybe I can have a function that transforms the data. And I could use dblink to call that function in parallel. So I can kind of build out a parallel batch processing system by setting up a few Postgres nodes and using the extensions. And then I can kind of also think about trade-offs. So here, maybe the central coordinator node, like whenever I do something, I might have to, when I do a Postgres FTW query on the nodes table, it actually needs to go to the coordinator node. So if my coordinator node is not available, that's not so nice. But perhaps I could use another extension for that. Or like pglogical, I could continuously push, replicate the changes from the coordinator to all the nodes. And even if the coordinator is temporarily down, I still have the copy on all the nodes, so I don't depend on it. Or the extension I discussed last year could be pgpaxos. I could actually replicate the nodes table in a consistent way among all the servers. Also, what I find useful in kind of setting up a distributed systems architecture is a way for nodes to act autonomously. So I wrote this extension pgcron, which is literally just cron in your database. So I took the source code written by Paul Fixie and copy-pasted it into a Postgres extension. And it kind of runs as a background worker alongside Postgres. And it kind of internally uses libpq, so it can actually run many jobs at the same time. And this is useful for, let's say, if you want all your nodes to do something every 10 minutes or every minute, or clean up old data, or apply some transformation. So it's also a tool you could use. And there's Citus, my day job, where it kind of gives you a way to already set up a distributed system out of the box. So you have in Citus a coordinator and then what we call worker nodes. And if you can call create distributed table on a table in Citus, and that creates shards on the worker nodes, which are just regular Postgres tables, and then queries are delegated to those shards. You can actually also use Citus in this way, where all the nodes have a distributed table. So then you can just connect to any node, and any kind of, let's say, insert you do on that distributed table will get routed to the right shard. And then actually Citus also starts acting as a kind of a middleware. I now have a shared data structure across all my nodes, which I could actually even use for kind of inter-node communication. Like one node could insert something into the events table, and another node could select from that table in a kind of consistent way. So it's another tool I can use for building out a distributed architecture. So, okay, so we kind of know our tools, or have at least gone over them briefly. So could we use that to build kind of an advanced distributed system using just Postgres extensions, and without kind of even external code? So I was kind of thinking of doing MapReduce and Kafka. I realized Kafka was going to be really difficult and MapReduce a lot simpler, so I decided to do Kafka. So how do you build a streaming publish subscribe system, what Kafka essentially is, on top of Postgres? So you have producers, kind of web servers maybe, that generate events like someone clicked this button or someone looked at this page. That goes into a layer, a kind of scalable layer of Postgres nodes. And then on the other side, there's consumers that kind of want to get a stream of events. Maybe they want just the clicks, maybe they want all the events. And they kind of want, ideally, exactly once delivery, or at least once delivery, but ideally exactly once delivery. So yeah, how do we get started? So there's actually, Postgres offers you actually many ways you could go about doing this. So I'm just going to describe one, which kind of works, just to kind of get to, within one talk, an entire Kafka replacement. So first thing I need is a way to store the incoming events that the producers are putting into my system. And I kind of want also be able to scale this out. So if I have many producers generating many events, I need a lot of bandwidth. So I could use Citus for that. And I can create a distributed table across all the nodes such that producers can just connect to any node and then do an insert on that table, and the data will get stored in the shards. And what's nice about using Citus here, if I want to later do something with this events table, I can add columns, and it can also manage rebalance operations for me. So that's a good start. But I mean, it's not Kafka yet. But so to set this up, I would create an events table. And I'm going to have a serial, which is to generate the event ID. I'll add a timestamp. It's often useful. And a topic name and a just generic JSON-B payload. And that's going to be where I put all my events should be in that form. Then I create the distributed table on the coordinator. And then I can PSQL into any node and kind of insert into events table or copy into the events table if I'm a producer. So I kind of do need to think a bit about some trade-offs here. So if I use the event ID, which is a big serial, as the partition column, then every event, like say I do a copy command, every event might need to go to a different shard. And this is very beneficial for optimizing data distribution, because my data will get evenly distributed across all the shards. But maybe alternatively, I could decide, maybe the application should decide which shard the data goes into. And there's some extra token like a stream ID, and that determines, okay, these events should go to this particular shard. Or I could do something a bit hackier, but also could be beneficial, where I make Citus pick a value for the partition column itself, and it should be a value that's on the local host. And the advantage of that is that if I'm a producer and I connect to a host, I know I'm going to be able to copy all my events into it because I don't need to connect to any other node to be able to write them. So for the remainder, I'll go with event ID for the kind of even data distribution. But it's like, there's some trade-offs there. So now on the producer side, okay, I connect to a random node. I can probably put a load balancer in front of my Postgres nodes to make it easier. And I do maybe a copy or an insert, and that copy will get fanned out to the shards, which are Postgres tables. Okay, so that's the producer side. I have a way for events to come into my system. I can scale this out. Now, how do I actually go about consuming those events? Like reading a stream of events. So in Kafka, you have this notion of consumer groups. So And a consumer group is a group of nodes that together want to get the stream of events exactly once. So you can have multiple consumer groups which all independently are consuming a stream of events. But within a consumer group, I can have multiple nodes, and I want to load balance the streams of events across the nodes. So, and actually, I'm just taking heavy inspiration from Kafka. So the way it works in Kafka, the consumer nodes kind of lease a partition, or in this case, we call it a shard. But actually, Kafka uses the same model. It uses multiple shards per node. And so when a consumer kind of starts reading from Kafka, it kind of tries to get leases on a shard. And that makes it the only node who can, at that time, consume events from the shard. So I will need to have a bit of infrastructure for managing that in my Postgres system. So in Kafka, the way this is done is via Zookeeper. So it's kind of a highly available consensus store. Now, I could have set up maybe PG Paxos for this as a highly available replicated table. But I decided it was simpler to do something kind of a bit more probabilistic. So I created a separate table on every node. So every Postgres node independently keeps track of the leases of the shards it contains. And this node keeps track of, OK, this is the consumer group, this is the shard, this is the current owner, and it also has a new owner column. And we'll use that for kind of handoffs, because if we're going to switch a stream, like one node is consuming a stream, and now a new node joins the system, and it wants to consume the stream, we don't really want to consume the events twice. We certainly don't want to consume them less than once. So a way to organize that is to say, OK, the current owner can finish its current batch, but once it gets back, we switch to the new owner. And so I have to keep track of both of these pieces of information. And I keep track of like when was the last time the kind of consumer reported. In case the consumer goes down, at some point I need to kind of make sure another consumer picks it up. So I need a way to get a lease. If I'm a consumer node, I connect to the Postgres cluster. I need to be able to say I want to like get a lease on a shard. So for that, I can define, utilize PGSQL and create a function that claims a lease, which essentially just boils down to doing an upsert into the leases table. If there's no lease yet, great, I get it. If there is a lease, then I set myself to the new owner. And here's another case where kind of Postgres actually solves a tricky concurrency problem for us. Because what if two consumer nodes are trying to grab the lease at the same time? Well, I can just add a filter where lease's new owner is null. So this will only do anything if there isn't already someone else who's trying to claim the lease. And Postgres takes care of the locking that's required for this. But actually, it's a bit inconvenient if all the consumers kind of need to figure out themselves like how to claim or which shards to claim. And so I also added a function for kind of automatically obtaining leases. And this gets, using dblink, all available lease tables, all available leases. And by available, I mean if a node is down, it just kind of ignores it. And if there's any shards which don't currently have a consumer node in the consumer group, then it claims those shards. If then it still has less than number of shards divided by number of consumers, it starts claiming or stealing random shards from other nodes. And so this is a very kind of probabilistic distributed algorithm. So the idea is eventually this will converge to all the shards having, or all the consumer nodes having either a number of shards divided by number of consumer leases or number of shards divided by consumers plus one. Because once you go over it, you stop claiming new leases. So one idea is you keep calling this function, and that's how it converges. It's a little tricky, but it kind of tends to work. Yeah, the only edge case that I didn't cover is like if there's more consumers than shards, this breaks a bit. But So if you're a consumer node, so this could be any kind of application that wants to do something with the data, could be just consume the data, put it in some other data store. What should it do? Well, first it needs to obtain leases. So this function is on one of the Postgres nodes, so it connects to a random Postgres nodes, calls obtain leases, and then that will use dblink to get the lease tables from all the other nodes, and then it will call the claim leases function. So after that operation, basically this one consumer node has the permission to get the events from all the shards. But we might actually, one consumer node might not be enough if we have a large stream of events. I mean, one of the most important functions that Kafka really fulfills is helping you scale out other parts of your system. Not only does it scale out itself, it also helps you scale out like your consumer layer and your producer layer. So we also want to make sure if we have multiple consumer nodes that the other consumer node also gets some to read from some shards. So it does the same thing. It calls obtain leases. It sees, well, all shards already have an owner, but I'm going to steal some random leases until I have number of shards divided by number of consumers, which in this case is 3. So I'm going to steal 3 leases from the other node. And so then, okay, we've divided the leases among the consumer nodes this way. And actually because they should keep calling this function like periodically, if let's say one of the node goes down, at some point the remaining node will actually claim all the leases. Or if we add a new node, it will start stealing leases from the other nodes. But at this point, leases is still a bit of an abstract concept. Okay, so a shard has an owner. What does that actually mean? What does it get to do? And so we have to decide on a way for like how do the consumer nodes, which is just some random client, how do they actually get the information from the shards? Like we kind of want to see all events that the producers are putting into the system, and ideally we want to see them exactly once. So one thing I could do is I have kind of serial numbers. Maybe I could keep track of up to which serial number I've consumed the stream of events. But that has some issue that you run into some concurrency issues where you're not actually sure if you see serial number 10 that there might not be a serial number 9, and that could mean that the transaction that generated serial number 9 aborted, or it could mean it's still in progress, and it's a bit hard to know which it is. So without adding more locking. So doing it at the SQL layer is actually a bit tricky. But again, actually Postgres provides exactly the feature we need, namely logical decoding. With logical decoding, I can just see a stream of all the incoming events and kind of gradually move forward in that stream. And actually I have a few different options of using it. There's some utility functions, SQL functions inside Postgres that kind of read from the logical decoding stream. I could use a replication connection. It's probably the best way to do it, but it takes a bit more effort. So I'll actually do the second one. Once I have Postgres 10, I could use logical replication. Limitation there is like the consumer kind of also needs to be Postgres. So if I want, I don't know, some random Ruby applications to read from my system, I have to use one of the other ones. So for simplicity, I'll go with the logical decoding utility functions. Namely, I believe it's called PG logical get changes, PG logical slot get changes, and peak changes. They're not super efficient, but for prototyping, they're actually great. So then I can define a function, and you can define this whole function in PL/PGSQL if you want. Which first, basically, this is the function for getting events from the stream of events. First, it checks if the node still has a lease, so it hasn't, like its lease hasn't been stolen. If it has been stolen, it just doesn't return any events. And it sets the owner to complete the handoff. It gets all the pending events using PG logical slot peak changes, and then it moves forward in the replication stream. So it uses replication slots for this, and they help you kind of make sure that you can kind of see all the recent changes to the database. And if for some reasons you weren't able to process those changes, it allows you to kind of keep them until you actually do. So this goes through the step: get the pending event, move the changes that we've processed forward, and then return remaining events. And the way we keep track of progress is the poll events function actually, as a parameter, takes the event ID of the last event in the previous batch. So that's my way of telling the system, like, hey, I'm done processing this batch. I've seen this event. So give me the next batch. Don't give me the same batch again. So this is something I can also implement in SQL. And the consumer can then, and this is, if you go to, like, say, Kafka docs, you'll see pretty much the same description. You need to always implement a loop, which first calls poll events. And actually, in the client library, it kind of polls all the shards. So in this case, if we're building a client for the system, the client library should make connections for all the shards on which the consumer node has a lease, and then call poll events. And then as it processes events, it keeps updating the parameter to move forward. And it just keeps doing this forever. So failure handling. So if you fail to connect to one of the nodes, if you're a producer, for example, you could just connect to a different node. You could have a load balancer in front of it to manage all that. Like storage node failing it's a bit tricky. That's like one of the areas where Postgres lacks a bit as a distributed system. Like the auto failover isn't built into the database. But I mean, you can't afford to lose events. So you need ultimately some sort of failover mechanism for your storage node. But at least for purpose of write availability, if you use the always copy into the local node trick, then you can always find some node that's available for your writes, at least. If a consumer kind of connects to a shard or connects to a Postgres node, tries to pull a shard, but then fails, that's not a big deal. It can just connect again and get the same batch, because the set of events that it gets will not change until it's actually confirmed the last batch. Now, if a consumer fails, it does not come back. Well, the idea is that the consumers periodically try to keep calling this obtain leases function, and then ultimately, and then also we need a way for expiring the old leases. So if a consumer hasn't reported to the system for a couple of minutes, we need to throw it out. And that's something we can do with pgcron. We can create a function that flushes out all the consumers that are no longer responding, and just run that every minute. And we could also do other things using pgcron, for example, like deleting alt events after a while, like after a day. So, okay, this was a complex system, right? But actually implementing this on Postgres, or at least prototyping it, is really not very hard. I wouldn't recommend writing it in PL/PG/SQL, but if you do, it takes maybe 300 lines of code. Because all the kind of functionality that you would normally have to write to have a kind of fault-tolerant distributed system, a lot of it is already there. So I have a little demo of the system I described. So I set up on EC2, let's see here, some like little cluster. So there's 4 nodes. There's just the Citus coordinator. And I also have 2 consumer nodes that are going to consume from the event streams. So my connections are still alive. Yes. Not super alive. That is a pity. Come on, Wi-Fi. Oh. Maybe if I put it here, it helps. Maybe a bit. So I'm typing, but it's not showing up. So basically, the nodes have a load balancer in front of them. So I want to try and connect to the load balancer. slow. And here you can see, so I'm connected to one of the Postgres nodes. I can see the shards that site has created. These are the shards that the events will be, the tables that the events will be stored in. I have the main kind of events table. So that's the one that the producers will write to. And I have a little script actually that will kind of connect to the load balancer and then just start inserting. Also suffering a bit from latency. OK, so now some events are going into my system. Now I'm going to act as a consumer. So I'm going to do obtain leases. I'm just going to be the only, so I'm the client now. I'm going to be the only consumer. I obtained 32 leases across the whole system. So this obtain leases function called all the other nodes to get leases on them. And now that I've done that, I can start polling for events from this node. And so I need to, so I can call the poll events function to get all the new events from a particular shard. Yes. OK, cool. And so the way this function works is, so if I'm programming a client, I take the last event in the batch and then pass that as the parameter. And then that's how I move forward. So now I get new events after this batch. But if something fails and I kind of reuse this value, I get the same events again plus any new events, and it goes up to batches of 100 rows. So on the consumer nodes, so the consumer could be anything. Like this is kind of the logic that the consumer library needs to implement. But I could also just implement that on Postgres. So I did that here, where I set up to consumer node. And by the way, I kind of want to show the code, but the latency isn't really letting me. Whew. OK, so this is a consumer node, but this is a Postgres node. And so this node wants to get a stream of events, process those events, and then move forward in the stream to process the next batch of events. And so the first thing I need to do is obtain the leases. So I can do that by using a dblink stub to call the obtain leases function in the system. So if I call this function, it tells me that I got 32 leases. So this consumer node is now consuming all the events. And I have a consume events function that will actually call the poll events function on all the shard of which it is the owner. So all the new events in the system will now go to this, will be returned by this function. Slowly. So I had about 121 events so far in the system. And actually, this function also keeps track of how far it has progressed along in each stream in its own local leases table, which will show up soon, hopefully. Yeah, so it keeps track of, OK, actually from this shard, I've consumed up to this event. And that's how it moves forward in the stream. And so I could also add another consumer. Oh, that's surprising. So this is node 2. It's now also going to obtain leases. And it's actually obtained 16 leases. So it's going to pull 16 shards. And so now actually the events are getting distributed across the two nodes. There's no actually nice way of showing that. But basically, they're now getting distinct events from these 16 different shards for which they are owner. So you should be able to see different events on both sides, but it's all random data, so it's a bit hard to show. And what's nice is I can actually, in this architecture, guarantee exactly once delivery, because I could even do something like begin consume nodes or consume events. And then, well, now my top event is 4 minutes past 10 and 28 seconds. Now, if I abort, I kind of ignore all the events. And then if I consume events again, I still get the same batch. And if I call it again after a commit, I get a different batch. So I can actually guarantee exactly one's delivery because my consumers are transactional. So it's a bit of a crazy way of implementing Kafka, but I'm kind of using it as an example to show how you could implement a fairly complex distributed system on top of Postgres. And the code for it is, well, there's this function, which consists of about 7 SQL queries. This is the obtain leases function. And then there is the poll events function down here, which is also about 7 SQL queries. And that's pretty much all the logic that I showed. And then the consumer is pretty simple. It mostly does a couple of dblink calls. So with relatively little effort, and you can find a link to these files in the slides that I'll put online. My presentation also has latency. So in the slides, you'll find that link where you can see it. But so my main point is that this is a real possibility. So you don't necessarily always have to deploy a new system to solve or a different system for every problem. You could actually build advanced, fault-tolerant, scalable systems on top of Postgres using all the tools that are available. Any questions? I'll take the question, are you crazy? Yep. It's convenient because it doesn't require kind of creating the schemas. So it's a bit quicker in that sense. But yeah, and sometimes you can express a bit more complex things with it. I'm not, well, I mean, like I'm calling functions, for example, like this RPC where you're doing a select function call, and then you could only do that using dblink. You couldn't use that using Postgres FTW. Unless you do really crazy hacks where you use like a default column and you do an insert, but don't do that. Any other questions? All right. Thank you very much.